morning, everybody. Welcome to our continued discussion of integrals. Okay, today we are going to talk about solving a differential equation, which I know sounds a little bit intimidating. I always remember when I was in college, like there's a class called differential equations, and I remember dreading having to take that class because it sounded so insanely difficult. And it turns out you pretty much already know how to solve differential equations. You just don't know it yet. So it sounds scary, but no worries. It's actually pretty easy. Well, easy, you know. Okay. So a differential equation is a really fancy word for an equation that has a derivative in it. And you may be thinking, that's nuts, Britton, but you've been dealing with differential equations already, because every time you took a derivative from day one, you were writing a differential equation. When you write dy dx equals cosine x, that's a differential equation. It's an equation, it has an equal sign, that has a derivative in it, dy dx, differential equation. How about that? Okay, so when we solve a differential equation, that means finding the set of function that satisfies it. And you've done that as well too, right? Finding the set of functions that satisfies that differential equation is figuring out what functions have that derivative, right? To solve that differential equation, we need to say whose derivative that is. In other words, what y equals equation makes that equation true. We've done that too. We called it an integral. All right, to solve a differential equation, all we have to do is do an integral. So if I integrate both sides of this, I find out, which we already know whose derivative this is, right? This is y equals the sine of x plus c. Okay. I already knew that, right? We had that memorized. But how does it go there? My face, okay, there it goes. My face disappeared for a second. All right, so we call this a general solution. It has a little plus c there, right? Now, again, this is one we already know. But I want to talk to you a little bit about when we're solving differential equations, the mechanics of this, right? So one of the things that we talked about when we first started looking at integrals was that dx. And we said that I called it your license to integrate, right? And I said, you don't actually have to do anything with it, but it has to be there. Right? So when we are taking dy dx and saying, I want to solve this differential equation, in other words, we need to integrate it. You can't really integrate this as it sits. What we have to do is a quick rewrite, right? So what we do here is we take that dx that's under the dy, we treat dy dx not like one quantity that stands for slope, but rather as a quotient or a ratio of two quantities, right? So I'm going to treat dy and dx as two separate quantities. I'm going to leave the dy over here, tiny change in y, and then on the other side, cosine x, I'm going to multiply the dx over. And I want you to notice what that does for me, right? Now I've got something over here I can actually integrate, and then we push this rule to the nth degree and say I can do anything I want to an equation as long as I do it to both sides, right? So I'm just going to integrate both sides. So I get the integral. Technically there's a 1 there, but we don't write it, right? And then the integral of cosine x dx over here. Well, the integral of 1 dy is your y. The integral of the cosine is sine. Okay, so this is what we call a differential equation. Technically it's called a separable differential equation. We'll talk about why that is. And to solve it, we integrate it. This is called the general solution because it's a whole family of functions. So we call it in general, if you take a function in the form y equals sine x plus c, dy dx equals cosine x is what you get. We call that the general solution. And that's what we've done so far. We didn't call it a general solution. We didn't call it solving a differential equation, but you've done that. Okay. What we have not done, though, is worked with situations where we're given an initial condition. In other words, saying, okay, whose derivative is this? And also not just whose derivative is this in terms of what whole family of functions would give me this derivative, but they give us another piece of information and they want to know specifically what member of that family. So in the previous example, sine x plus c isn't enough. They want to know which vertical shift of sine it was specifically. And we can figure that out if they tell us just 1 point on the original function. And that's what they've done here. Okay, so if I want to solve this differential equation, I can take my dx and multiply it to the other side, right? So I have dy equals 3x squared plus 4x dx. And then I can say, okay, I'm going to integrate both sides. All right, so I'm going to put a 1 here. The integral of 1 dy is just y. Over here, 3x cubed over 3 plus 4x squared over 2 plus c. All right, so I end up with y equals x cubed plus 2x squared plus c. This is my general solution, right? This is this entire family of functions. All the functions in this form, remember, all the c does is give us a vertical shift of a function. All the functions in this form are going to have this derivative. In other words, at any given x value, all of these functions are going to have the same slope. Because all the c does is shift it up or down. All right, but we want to know which one of the members of this family passes through exactly the point 0, 3. Okay. This reminds me of when you use y equals mx plus b to write the equation for a line, right? Because you have to plug in your x and y value, and then we'll figure out what c is, and then pop it back in, right? So that's all we're going to do to solve to use this initial condition and get what we call the particular solution. Okay, so I know that y of 0 is 3. In other words, I know that the graph, the particular function I'm interested in, contains the point 0, 3. So all I have to do is come over here and say, okay, well, when y is 3, x is 0, so that means c must be 3. So my final answer here, what we called our particular solution, is x cubed plus 2x squared plus 3. Now, we will see questions that say, and it sounds like a lot, they'll say, find both the general and the particular solution to the differential equation. We just did that. We found the general solution here with the plus c on it, and then we plug in the point, figure out what c is. That's my particular solution. Okay, general has the plus c on it. Particular, we figured out what the c is. And that is solving a differential equation. Congratulations. We also call those initial value problems sometimes because you're doing an integral, but they've given you an initial value. So now you're able to find out c. Now you're able to give a more specific answer. All right. So here's another one. Take a moment, try it, and we'll get back together on it. Okay. So first thing we're going to do is multiply this dx to the other side. So I have dy is equal to sine x times dx. And I'm going to come in here and I'm going to integrate both sides. Again, I can do anything I want to an equation as long as I do it to both sides. So I'm going to go ahead and do that. Integrate on both sides. And again, you can put a 1 in here if it helps you to remember what you're doing over here. You're integrating a 1 on y, so it's going to turn out to be y. And then we're saying, whose derivative is this? Okay, well, the derivative of cosine is negative sine, so this must be the derivative of negative cosine x. And then there's a plus c. Okay, this is my general solution. So now that I have my general solution, let's plug in and find our particular solution. Let's do it in green. Okay, so I know that when y is 0, or I'm sorry, when x is 0, y is 2. So I know that 2 has to equal negative cosine of 0 plus c. Okay, so we know, of course, the cosine of 0, give me trouble. The cosine of 0 is equal to 1, right? So I have that 2 is equal to negative 1 plus c, which means, miraculously, c is 3 again. I promise you c isn't always 3. Okay. So now I know what c is. I can go back up and do my particular solution. So now I know that y is equal to negative cosine of x plus 3. That is my particular solution. Now, I like this example because it points something out that is a pretty common mistake. A lot of times, when we're trying to solve an initial value problem, people see an initial condition with a 0, and they assume that when they plug in a 0, everything but the c is going to come out to 0. And so instead of actually chugging it through, they just think like, oh, that's easy. I know this. The c is going to be 2. Be really, really careful. That's only going to be true if you're plugging it into like a polynomial. Remember things like e to the 0, that comes out to 1, right? Or if you have a rational function, just because you're plugging in a 0 doesn't mean it's going to come out to 1. And it's especially true with trig functions as well. Just because you're plugging in a 0 doesn't mean it's going to come out to 1 or 0. So be careful. And don't just assume that if your x value is 0, that your y value is going to be 2. I know that might sound silly, but people do it all the time. So just kind of keep that in mind. You have to make sure you plug in and get the actual c value. Don't just assume that what they gave you is your c value. All right, so again, we've done this before. The only real layer we're adding here is figuring out the c value, which is just a little bit of arithmetic. All right, so I want to show you a couple examples of how they can kind of throw a wrench in this, because of course it can never just be as easy as do an integral and figure out what c is. All right, so this first example here, this came up for us. Somebody had asked when we started taking integrals if we can take kind of higher order integrals in the same way that we took higher order derivatives. And I said, well, we kind of can, but we kind of don't. This is the one example where we do. It's not something we see particularly often, but we see it enough, right? So notice that what they gave me here wasn't a derivative, but a second derivative. Okay. So if I integrate y double prime, I'm not going to get y, I'm going to get y prime. And then if I integrate y prime, I'll get my y function. So when they say solve the differential equation, they want my answer to be a y equals. Well, to get from y prime to y, that's 2 steps. So notice that they had to give me 2 conditions. They had to give me 2 points. They had to give me a point on my derivative so that after I integrate the first time, I'm able to find out what that c value is. And then they had to give me a point on my original function, so when I integrate the second time, I can figure out what that c is. And it's important that you keep track of that c along the way, and don't just wait till the end and throw a plus c on the end, right? Because if you do that, you'll get the wrong c. So I'll show you what I mean. All right, so let's take our second derivative here. And I know that if I integrate the second derivative, I'm going to get, oops, sorry. If I integrate the second derivative, I'm going to get the first derivative. So that is the integral of 20x cubed plus 6 dx. So y prime is 20x to the 4th over 4 plus 6x plus c. So my y prime is equal to 5x to the 4th plus 6x plus c. And here's what we know. If you plug in a -2, you should get a 68. Right? So I can figure out what this c value is immediately, and I need to do that now. Right. So let's see. I should get a 68 if I plug in a -2. So 16 times 5 is 80. Oh, look at that. Jerks. So this is 80, and this is -12, which just happens to be 68. So little magic there. That c is 0. That's actually really lucky, because if that c wasn't 0 and you didn't do that step, ooh, would you be in trouble? All right, but the good news, that did come out to 0. So here's what I know. My derivative is 5x to the 4th plus 6x plus 0. I'm not even going to write the plus 0. But I'm not done, because that's just the derivative, and I need second derivative, or I need the original function. I'm starting with second derivative. I need to back up to my original function. So I solved a differential equation, but I ended up on a derivative, not a function. So let's do it again. So if I integrate my derivative, I'm going to land on y. So y is going to be the integral of 5x to the 4th plus 6x. So that would be 5x to the 5th over 5 plus 6x squared over 2. And again, don't forget your plus c. Right. So I end up with x to the 5th plus 3x squared plus c. And they tell us that if you plug in a 1, you should get a 2. So I'm going to go up here. 1, whoops, 2 is equal to 1 to the 5th. That's 3 times 1 squared plus c. So 1 plus 3 plus c is equal to 2. All right, so if 2 equals 4 plus c, then my c must equal negative 2. So I can go down here and plug it in. My final answer is going to be x to the 5th plus 3x squared minus 2. Okay. Again, when they say solve the differential equation, what they mean is to get it all the way down to y equals, and there should not be any c's in there. Okay. Now, I have seen people, I have no idea why you would do this, but I've seen people do this. Hey, do your thing. That instead of finding the c, instead of integrating, figuring out what c is, integrating again, figuring out what c is, they leave the c in, and they do the integral, and then right here they put c1. They call this c1. And so over here there's a plus c1 because they didn't do this step, right? They didn't bother to figure out that c is equal to 0 and that they don't have to carry it along. So then when they integrate here, they end up with a plus c1x. And then they say plus c2. So they have a c1 and they have a c2. And then in the end, they do like a system of equations to figure out what their constants are. Make your life easy. Just find the c's along the way. Integral, find c, integral, find c. You're done. Now, they could give you a third derivative and ask you to work it back. As long as they give you a condition for the second derivative, the first derivative, and the function, you should be able to do it. They could give you a 10th derivative and ask you to work it backwards. As long as they give you a point on the 9th, 8th, 7th, 6th, 5th, 4th, 3rd, 2nd, 1st, and original function, you could do it. It's a pain in the butt. They're not going to ask you to do that, but they could, right? You could always work it back as long as you have a point on each one of the derivatives in between the derivative they gave you and the original function. Okay. You can always work it back. All right, so this is kind of one way they throw a twist in it, right? They make it a second derivative or a third derivative or whatever. This is my just kind of another way they throw it at us. Notice it just says, which of the following is the solution? They give you the differential equation, and they give you an initial condition. What I want you to notice about this one is that it's implicitly defined, right? So again, somebody had asked about, do we do implicit derivative or integrals like we did implicit derivatives? And the answer is no, we don't. We don't integrate implicitly, but what we do is make sure before we integrate that we've gotten the x's and the y's away from each other, right? So again, I'm going to multiply my dx to the other side here, but notice there's a y sitting there. So what I'm actually going to do is do like a little cross multiply. So I will end up with y dy on one side and x squared dx on the other side. We call this a separable differential equation because I'm able to take all my y's and put them on one side with my dy and all my x's and put them on the other side with my dx. Okay, so this is adding a little twist to it because now when I integrate both sides, this is no longer just a 1 dy over here. It's going to be a y squared over 2. Okay, so I'm going to do y squared over 2 on this side. And then over here I'm going to have an x cubed over 3. Now, notice I only added a c one time. Okay. I want to point that out because there's nothing special about integrating x versus integrating y. Okay. It's just that if I had written y squared over 2 plus some constant equals x cubed over 3 plus some constant, in the end what I have is an equation that has two constants. And those two constants can be combined into another constant. So if you want to write c1 and c2, and then in the last line say, oh, c1 and c2, I move that over and they combine to be c3 or whatever. You could do that. But there's no reason to. As long as you add one constant, if you integrate the left and integrate the right, as long as you add a constant to one side or the other, you should be okay. All right, so I know that if I put in a 3 for x, I should get a negative 2 for y. Now, I'm not going to solve this out yet. I'm going to go ahead and put my initial condition in first. So I'm going to put in a 3 for x and a negative 2 for y. So if I put in a negative 2, all right, so 4 over 2 is 2. 27 over 3 is 9 plus c. So I get that my c has to be a -7. Okay, I want to give myself a little bit of space here. So let's remember that, let's see if we can remember what our equation is so I can clear this. Y squared over 2, x cubed over 3 minus 7. Okay. Okay. So I have y squared over 2, I have 1/3 x cubed, and I have a minus 7. Okay. All right, so I notice this is not a, I'm kind of done here, right? I solved my differential equation. The problem is that none of these answers are in this form. Okay, so I need to just algebraically get my answer in the right form. So the first thing I'm going to do is multiply both sides by 2, so I get 2/3 x cubed minus 14, and then I'm going to take the square root to get my y. Now, really important here, if you're given a square root, you get to assume that it's the positive root, right? If the person who wrote the square root symbol wants it to be a negative root, or for you to consider the negative root, then they have to write the plus or minus. When you are the guy that takes the square root, right? When you're the person who comes in and takes the square root, it's your job to put the plus or minus on it. It's your job to consider both possibilities or both roots. So when I take the square root of both sides here, make sure you don't forget that when you take a square root, it's a plus or minus. Now, I'm saying that to you for a very specific reason. You may notice here, our answer, square root of 2/3 x cubed minus 14, is sitting right here, but so is the negative root. Right? And this is a little bit dirty, because if you forget to do the square root, you're going to choose D, and you're going to be wrong. Because look at the point they gave you. They said when you plug in a 3, what you should get out is a -2. So the initial value, this function that goes with this derivative, has 2 branches, right? It's about a positive one and a negative one. Well, if I put in a 3 and get out a -2, then I need to be on the negative branch. So the answer I need to choose here, based on the initial value that they gave me, is E. Right? So this to me, again, this goes against everything AP says. They say they don't punish you for algebra mistakes, but I think this is a prime example of punishing you for an algebra mistake. If you just take the root and forget to do the plus or minus, you're going to grab D, and you're going to be wrong. Because this is clearly saying with this initial condition that if you plug in a 3, you're going to get a -2 out. So that has to be the negative root. So a little bit tricky on that one. And again, not calculus tricky, algebra tricky. Okay, one more kind of a way that they get us, these tricky AP questions. They give us a differential equation, and they say find y if y of 2 is equal to 7. Now this looks at a glance like a simple initial value problem, right? Integrate, plug in, find c. No, and here's why. This differential equation right here is not a differential equation that we can solve. Okay, so I can't integrate this. And again, it's going to be our job to recognize when we have something we can't integrate, right? So I'm looking at this and I go, okay, well, if I wanted y, here's what I know. Y is equal to the integral of e to the x cosine squared x dx. So ideally, I could integrate this, plus c, plug in the 2 and the 7, figure out what c is. No, can't do that here. Because it's going to be our job to recognize that this is not integrable for us, right? Is that somebody's derivative? Absolutely it is. Do we know whose derivative it is? No, we do not. We could look it up, but we don't need to. All right. When they say find y if y of 2 is 7 in these instances, and usually I will say they give this to you as a multiple choice, because otherwise I don't think it's innately obvious what they would want you to do. One of the things that they're asking us, what they're really asking us to do here is find y, but there's going to be an integral in our answer. And again, that's why they tend to give it to you as multiple choice, because otherwise I don't think you would think that you were done if there was an integral in your answer. Okay, and we're going to talk tomorrow about another way that we could get at this y, another thing they might want us to do. Right? And it's our job to kind of read the cues in the problem and figure out what they want us to do as we get all these different methods. But first things first, we need to recognize that this is not an integral that we're going to be able to do. All right, so watch this trickery. Okay, here's what I want. I need to adjust this expression so that when I take its derivative and plug in a 2, I get a 7. That's what I need, right? I need to take the derivative of this integral, fundamental theorem, and when I plug in a 2 to my derivative, I need to get a 7. Okay, now, again, first time I saw this problem, I had to kind of work backwards from their answers to figure out what the heck they had done. So if you're thinking, how on earth would you ever think to do that? I don't have an answer for you. Let me get a different color pen if my computer will allow me to. Okay. I don't think my computer's going to allow me to. Blue it is. Okay, perfect. All right, so I want to take the derivative of an integral here. So I'm going to have a fundamental theorem. So in other words, when I do y prime, it's going to be the derivative of this and I need that to come out to 7. Okay, so check this out. Watch what they do. This is so sneaky. They say, all right, here's what I'm going to do. I'm going to define y as the integral of e to the x cosine squared x, but very specifically, I'm going to put limits on this integration. I'm going to define it, the limits, I'm going to have them go from 2, which is the number I happen to know, up to x. So when you take the derivative of this, it's just going to be e to the x cosine squared x, right? Because when I take the derivative of this integral, it's going to plug in your upper limit, chain rule, plug in your lower limit, chain rule. Because it's just a constant up to x, if I take the derivative of this integral, it's just going to come out to e to the x cosine squared x. But specifically, if I plug a 2 into this integral, properties of integrals, the integral from 2 to 2 is 0. So watch what they do. They say, okay, you want me to figure out what y is equal to? Okay, I know that y is equal to this integral. So watch this. I'm going to make my limits of integration go from 2 to x so that when you plug in a 2, this integral comes out to 0. But I don't want this whole thing to come out to 0. I want the whole thing to come out to 7. Oh, here, I'll fix that. That's honestly what they want you to do. I know that's crazy, and I know who would ever think of that. But again, you're usually going to see this as multiple choice, right? It's going to say which one of these is y equal to, and there's going to be a bunch of answers, right? This is the one you're looking for. And again, look what they did. All they did was they said, okay, I know that y is going to be the integral of this. Y is going to be the integral of this function. And then to fit in my initial condition, I make my integral go from my initial condition up to x so that when I plug that value in, given value in, my integral part comes out to 0. And then you take your y value and add it to the end. So that when we plug a 2 into this expression, when I do y of 2, this becomes 0 plus 7, and it comes out to 7. I know. All right, so again, this is usually a multiple choice type question. This is not something that anybody would expect you to kind of think of on an open-ended, but it gets to the fundamental theorem of calculus, and it gets to those properties of integrals, and it gets to the initial condition things, so it's kind of a loaded problem. All right, now, the next time we talk, we're going to talk about a little bit more about what to do when we have a differential equation that we can't solve. Right? What are we going to do when we are given a differential equation and we can't get it integrated? Right? And there's some stuff we can do. So we will talk about that the next time we see each other. All right. Have a wonderful day. I will see you soon.